Okay, so to finish chapter 2.2, we are going to do one of the problems in the problem sheet, which covers all of the material we studied. And this will help you understand all the concepts. So the problem is the following. Consider the transformation given by the matrix A equals 1 minus 2, 2 minus 4. And basically I'm asking you to write down the input space, the range, the null space, the dimensions, the theorem of dimensions, everything, okay? So let's do it. So for that I have prepared the applet where I have written here the matrix 1 minus 2, 2 minus 4, and you can see here how it is applied to different vectors, and you can see that it is a very strange transformation. Yeah, it's not easy to say what this transformation is doing. It's not a rotation, it's not a projection, it's something strange. So from intuition, I cannot give you the null space and the range. We have to calculate them using maths. Okay, so let's do exactly that. So we will start by writing down what is the input space and the output space. So input space is simply two-dimensional space, right? Because this is a 2 by 2 matrix, so it acts on two-dimensional vectors. So the dimension of the input space, n equals 2. It is also the number of columns of matrix A. Okay, the output space is also 2D space, so m equals 2. Now, what is the range of the matrix A? So let's use the definition. The range of A equals the span of the columns of A. And this is equal to the span of the first column of A, which is 1, 2, and the second column of A, which is minus 2, minus 4. So this seems to be like a plane, right? Unless the two vectors are linearly dependent. If the two vectors are linearly dependent, then their span is not a plane, it could be a line. If they are, for example, if they are parallel. So you could check if they are linearly dependent using the usual methods of solving a system of equations, or with some intuition you can notice that if you multiply the elements times minus 2, you find the second vector. Therefore, these two vectors are parallel, so they are linearly dependent. Which means that the second vector is redundant in terms of the span. So the range of A is equal to the span of this first vector, 1, 2. And the span of a single vector is very easy to write, is simply lambda times vector 1, 2. So it's the equation of a line. This is the parametric equation of a line. Yeah. So what is the rank of A? The rank of A is the dimension of the range of A. And since the range of A is a line, this is 1. Okay? So that's it for the range. Next let's calculate the null space of A. So the null space of A equals the solutions x to ax equals 0. That was the definition of the null space. So let's solve that system of equations. Let's solve a times x equals 0. In this case, to match the notation I use in the problem, instead of calling the vectors x, I'm calling them v. It doesn't matter. So we want to solve a times v equals 0. So I write a, which is 1, 2, minus 2, minus 4, multiplied by vector v. Now, vector v has two components, so let's give some names to the components. It will be the x component and the y component. Yeah. So this is equal to 0. So if we do the matrix vector multiplication, we find out this is a system of two equations with two unknowns. So what is the system? The system is x minus 2y equals 0 and 2x minus 4y equals 0. Yes? So we have the system of two equations and two unknowns. Let's call this equation 1 and equation 2. And the two unknowns are x and y. So if we now do 1 minus twice equation 2, sorry, we do twice equation 1 minus equation 2, then what we get is actually that 0x plus 0y equals 0. So we end up with 0 equals 0, which means that one of the two solutions is redundant. So one of the two equations is redundant. Okay? So this means that we can just use equation 1 to find that x minus 2y equals 0, and therefore x equals 2y. And this is our general solution to this system. So x equals 2y is the equation of a straight line, yeah? But easy way to see this is to write vector v, which is equal to xy, and substitute the general solution into vector v. So then this would be 2y and y, which would be equal to y times vector 2, 1. And what is y? Y can be anything. Any value of y would give us a solution to this system. So actually we could say that y is a free parameter. And we could call it lambda, as we usually do with parameters. Yeah. So this is equal to lambda times vector 2, 1. And this is the parametric equation of a line. Okay. So either by noticing that this was the equation of a line, or here by noticing that this is the parametric equation of a line, it's the same line. Okay. This is the general solution to the system a times v equals 0. So what is this would be the null space of A. What is the nullity of A? The nullity of A is the dimension of the null space. And since the null space is a line, the dimension is 1. So is the theorem of dimensions fulfilled? So we have that the rank equals n minus the nullity. So we know the nullity is 1, we know n equals 2, and we know the rank equals 1. So it is fulfilled. Okay? So we have calculated range and null space. Now this also asks us to draw all the subspaces in the two-dimensional plane. So let's do that. Let's draw the xy plane, which is the input space. And now let's draw the range. So the range is this line here. So it's lambda times the vector 1, 2. This is the parametric equation of a line crossing the origin and parallel to the vector 1, 2. So if this is 1, 2, 1, and 2. So a line parallel to a vector 1, 2, that is the range. So this infinite line is the range of A. Is it true when we use the applet? So if we look at the applet, so indeed it seems that whatever v I choose, the output A times v is always contained within this line, which is parallel to the vector 1, 2. So yes, this makes perfect sense. So the output is always in this infinite line. Okay, next, what about the null space? So the null space we found was equal to this line here, lambda times 2, 1. So this is a line that is perpendicular to the vector 2, 1. So it's, sorry, not perpendicular, parallel to the vector 2, 1. So it's this line here. So this line is the null space of A. Okay? So this means that any vector v that starts in this line will end up in 0. Let's check that in our applet. So if I start vector 2, 1, the answer is 0, indeed. If I do double that vector, answer is 0, 0, 0. So whichever vector I choose inside this line, the answer is always exactly 0. Okay, so that's the meaning of the null space. So any vector inside this line gets outputted as 0. So in that way, we have shown how to calculate the range and the null space of A. Next, this problem asks us to solve the system A times X equals V. So here we have to solve A times X equals minus 1, 2. Okay, how do we do this? Let's write down the equation, which is 1, 2 minus 2 minus 4 times vector xy equals minus 1 minus 2, minus 1 and 2. So this is a system of two equations with two unknowns. So it's x minus 2y equals minus 1 and 2x minus 4y equals 2. So we call this equation 1, we call this equation 2. And if we do twice equation 1 minus equation 2, what do we get? We get 0x plus 0y equals minus 2 minus 2 equals minus 4. So we get 0 equals minus 4. So this is impossible. So this means that this system has no solution. For x. Okay? And this makes perfect sense because this vector v that I gave you, minus 1, 2, let's look at it in the applet. So the vector minus 1, 2 would be here. And I'm asking you, what is the original vector such that the output goes there? There is no vector whose output goes to that position. So there is no solution to this system. Okay? Another way of explaining this would be using our Venn diagrams. So this is a transformation with a determinant equal to 0. Therefore, all of the input space is being reduced to a subspace, which is this range of A. So now what I'm doing is that this vector v that I chose here, this vector v is outside of the range. Therefore, there doesn't exist any vector x anywhere that ends up in this vector v, because all the possible vectors in 2D space end up inside the range. So since I gave you a vector v outside of the range, then the system has no solution. Okay? Next, solve the same system but with A times x equals minus 1 minus 2. So this time, this vector minus 1 minus 2 is inside the range of the matrix, right? Because the range of the matrix was this line, lambda times 1, 2. And if you substitute lambda equals minus 1, then you get minus 1 minus 2. So this point, this vector I gave you, is inside the range. Therefore, if you draw the input and output and you draw the range of the transformation, now this time I'm giving you a vector v that is inside the range. Okay, so how are you going to give me your answer? Your answer should be an entire subspace that goes into vector v. Okay, so let's see how this pops out when we solve the linear system of equations. So matrix A is this matrix times vector x, which is xy, equals -1 - 2. So this is a linear system of equations equal to x minus 2y equals -1, 2x minus 4y equals -2. So this is equation 1, this is equation 2. Then we do twice equation 1 minus equation 2, and we get that 0x plus 0y equals 0. So this time we get 0 equals 0. Okay? So it means that the two equations are giving us the same information. So we can actually get rid of one of the equations. So now we can look only at equation 1. And equation 1 is saying that x minus 2y equals -1. Therefore, x equals -1 plus 2y. This is the equation of a line. Yeah. So one way we can write the parametric equation of the line is to say y can take any value. Yeah. So it is a free parameter. So we can say that y equals alpha, or lambda, as we are normally using. And therefore, x equals -1 plus 2 lambda. And therefore, if we write our solution x, which equals xy, this is equal to -1 plus 2 lambda, that's equal x, and then lambda, because y equals lambda. Or we can write this in another way. We can write it as, we can split it into the terms that are independent of lambda plus lambda times 2, 1, right? And this is the equation of a line, the parametric equation of a line, where this is R0 and this is the vector v. So this is how we give the general solution for x. So I asked you to solve this problem, and the solution is not a single vector, but instead it's an entire infinite line of vectors. And now notice the following. This is a particular solution, what I called x0 when I was explaining to you the theory, and this is nothing more and nothing less than the null space of A. So remember, the null space was this line, lambda times 2, 1. This is the null space, yeah? So as I promised in the theorem I proved earlier, the general solution for x is equal to a particular solution plus the null space of A. And this is always the case. This is always like this. Okay, so I hope that with that, the concepts of this chapter are clearer with this very long and detailed example. And let me say one last thing. In the next chapter, which is 2.3, we are going to study linear systems of equations and how to solve them using a very powerful method called Gaussian elimination. And at the end of that chapter, I will show you how to calculate the range and the null space of a matrix in a simpler way. So basically, by solving using Gaussian elimination, you will see a technique of calculating the range and the null space, which is a bit easier than how I did it here. Okay, so thank you very much for watching.